This is problem 4 from the tutorial questions on page 21 of the course notes. So this is one of these problems where we're asked to draw a shear force diagram and bending moment diagram. And as is the case with some of the other problems we looked at in the course, we need to find some information about our forces before we can start to do this. So let's, before we even get into the calculations, have a look at what's going on in the question. So we're told in this question there's a point force of 10 kilonewtons been applied here, 2 meters from the left-hand side of the beam. And we're told that there's a uniformly distributed load of 9 kilonewtons per meter applied across the whole beam. Now we know in the question we sometimes have to consider just a section of beam, but if we just consider the whole beam for now, the beam is 2 plus 7, 9 meters long, and we've got a 9 kilonewton per meter UDL. So the total force acting down the way is going to be 9 times 9, 9 kilonewtons per meter times the 9 meters of beam. So it's going to be 81 kilonewtons acting downwards on the beam, along the length of the beam, but 81 in total. And that's something that's going to be important for working out the reactive forces acting up the way. To help us out here, we're going to give these a name as well. So as we often do, we'll call the left-hand side of the beam A and the right-hand side B. And we may as well call this point here C as well. Now, these are just names that we are picking. You don't have to name parts of the beam as long as your calculations are clear, or you could call them something else. I just think letters are most straightforward. So those are the points in the beam. And we've got a reactive force here. We'll call this VA, because it's V for vertical and A is the point A acting up the way. It's indicated with this arrow here. And we've got a reactive force VB acting up the way. And what we know is that these two forces added together must be the same as all the downward forces added together, because they balance, we know, because we have static equilibrium, that the sum, that's what this sigma means, sum of V is equal to 0, which means all of our upward forces must be balanced by all of our downward forces. So what does that mean? Well, it means, remember, if we take up as a positive direction, VA plus VB minus the 10 kilonewtons from the force being applied at point C, minus the 81 kilonewtons, this is the total force due to the UDL, is equal to 0. So our two upward forces must balance out our two downward forces. So that simplifies to VA plus VB is equal to 91 kilonewtons. Now, we don't have enough information from our vertical forces to say how big VA and VB are, but this equation we've determined here is going to be helpful to us shortly. In order to find out how big VA and VB are, we need to find one of the two of them, and there's two ways we can do it. So we can either get VA or we can get VB. And how we would do this is we consider the moments. Now again, because we have static equilibrium, it means the moment, the turning effect at any point in this beam must be 0. So any forces trying to turn the beam clockwise must be balanced by forces applied at a distance, that is moments, trying to turn it anti-clockwise. So at any point in the beam, we're going to have sigma m, the sum of all the moments acting is going to be 0. Now, we have the freedom to choose where we want to work this out. Now, we could pick point C and work it out there, but we're going to run into a problem because VB and VA are going to give us moments. So it's just going to give us another equation where we don't know two things in it. But if we pick point A or point B, we don't have to consider the forces acting there because we're only considering moments. So if we were to take, in fact, we will take point A for consideration, VA won't be part of our equation because A is at distance 0 from itself. So for a moment, if we were even going to consider it, we'd be multiplying by 0. So let's consider the sum of all the moments at point A. So this is sigma m at point A. This is also, again, 0 because the moment at any point in a static structure is going to be 0. So I'll tidy up our diagram here. I'll remove some of these drawings I've put on it just now, just to tidy things up a wee bit. So let's consider what's happening at A. So this is, circle this in green. This is point A, and we want to consider forces, how they're trying to act with a rotational effect. Now you can see here, if we imagine this A is our point that we're looking at, this force of 10 kilonewtons, if A to B is like the like a beam sticking out of a structure, of like the hand in a clock, looking from left to right here, the forces pushing down are going to be shifting the beam in a clockwise direction about A. So if we think about this force of 10 pushing down is pushing the beam down the way, and that's like it turning clockwise. So forces acting, all forces here are acting to the right of A, and the forces acting down the way will be having a clockwise moment, and the forces acting up the way will be having an anti-clockwise moment. So we know that those two things are going to counterbalance each other. So what does this look like when we put in our equations and our values? So let's move along the beam from left to right. Well, let's start off with our point force at point C. At point C, we have a 10 kilonewton force, and it's acting at a distance 2 meters away from point A. So it's 10 times 2. And we're going to have a force that's acting in the opposite direction due to VB, because that's pushing the beam up. So we'll say subtract, because that's going to be a counterclockwise moment, and that's going to be VB, that's the size, so the force we haven't worked out yet, times 9, because that's how far away it is. But there's a third force acting that we need to consider for a moment, and that is the force due to the uniformly distributed load. Now we know already that this is 81 kilonewtons, so that's how big it's going to be, and it's going to be a positive turning force, so we'll say plus 81. But what are we multiplying this by? Well, if you remember, we always consider the force due to the UDL for these calculations to be applied halfway along the distance we're considering. Now we're considering the distance of the full beam from A to B, so that point is going to be here, and that's going to be a distance of 4.5 meters, because that's half of 9. It's halfway along the beam, so it's 9 times 9, that's 9 kilonewtons per meter, times 9 for the length of the whole beam to get the total force. And then we're multiplying by the halfway point, which is 4.5 meters. So we'll put that in here as well. And we know this has to be add up to 0 because the beam isn't rotating. So we'll do a little bit of tidying up here now, get my calculator out and make sure that I'm getting this right as well. But we'll do it a step at a time. So we've got 10 times 2, well that's nice and easy, we've got 20 there, minus 9 VB, and 81 times 4.5. That's 364.5 equal to 0. Do a wee bit further tidying up here, and we've got 9 times VB is equal to, let me just get this right, 384.5. So VB is equal to that divided by 9, which is 42.72. That's the two decimals, 42.72 kilonewtons. So this, I'll just tidy this up again up here. So this force VB, by considering the moment at A, we've been able to say that that's equal to 42.72 kilonewtons. Now we could actually do the exact same process and consider the moment at point B, and that would tell us what VA was as well. But fortunately, we don't need to do that because of what we worked out at the start, what VA plus VB is equal to. Underline that twice in red. So considering that equation, VA plus VB is equal to 91. If we put in our value for VB, so we now have VA plus 42.72 is equal to 91, then we can subtract 42.72 from both sides and get VA equal to, I think that should work out at 48.28 kilonewtons. I'm going to double check that in my calculator. And yes, that's right. So we're happy with that, hopefully. So I'm just going to tidy things up a little bit again, just so that we can do a wee bit more work. So I'll remove that, remove this as well. I'll mark on our diagram what VA is equal to, so that's 48.28 kilonewtons. If you need to go back, you can obviously pause the video and rewind. So that's how we worked out what our other two forces are. I'm going to erase all of this just now, and we'll look at the shear force and bending moment diagrams. So if any of that wasn't clear, now's a good time to pause the video and watch that last bit where I did those calculations. So now we have all of our forces, and this leaves us with enough information to draw our two diagrams with a few other little bits of calculation. We'll start off with the shear force diagram, and as before, we will draw a line to represent zero shear force, which will also represent the position on the beam at which shear force applies. So a wee bit further down than that. Here, I think we'll do. We'll call that our shear force diagram, and remember the points at either end are on the line are zero shear force, and the line that is point A at the left hand side and point B at the right hand side. These do correspond to the same positions on our beam. So let's remember what we do with the shear force diagram. Well, we start off on the left hand side and we look at how forces are applied to our beam. So coming at the beam from the left, at point A, the very left-hand edge of the beam, we've worked out the previous part of the question that the force of 48.28 kilonewtons acting up the way. So that's what we're interested in. And that's the first thing that we're going to mark on our diagram. So let me get this. A bit too thick, that line. I'll make my pen a bit thinner. We'll say that will do. So that's us going up, and we're going to say that's gone up by 48.28. That's a positive force acting up the way in our diagram, 48.28. And what we then do, because we have a UDL, is we consider at each point force being added, what's happening just before we get to that point and just after we leave that point. So let's have a think about this. So consider point C next, point C. Just to the left of point C, so as we're traveling along our beam from A to C, like we're under an arrow here, we're traveling along here, and we get to this point just before this 10 kilonewton force is applied. So this is the point that's just left of C. What forces do we have in play? Well, we know we've got the upward force at A because we've included that in our diagram where it's got 48.28 kilonewtons. And we know we've got all of the downward force due to the UDL at that point. So we've travelled 2 meters along the beam to get to C. So we have a 9 kilonewton per meter UDL over 2 meters. So we've travelled 2 meters, so we have 2 meters worth of our UDL. So that's a total of 18 that's going to add up to. So if we put that into a simple arithmetic sum there, we're left with 30.28 kilonewtons. So we've come along to this part of the beam here. We've got 48.28 acting up, and just before we reach this 10 kilonewtons coming down at C, we've already accrued 18 kilonewtons acting down the way due to the UDL. Now what happens just as we pass C? So we've just got to C, just past C, so just to the right of C. Well, we still have these other two forces, 48.28 from point A. We still get 9 times 2 acting down from the UDL, but we've also now got the 10 kilonewton force from C that we've got to that point, and we're going to include it as well. And that's acting down the way, that's minus another 10. So that's just going to be 10 left in the answer above, so it's going to be 20.28 kilonewtons. So how we plot this on our shear force diagram is at point C, we plot 2 points. First of all, we plot a point about here, which is going to represent 30.28. And we plot another point here, which represents 20.28. And because they're at the same point, we draw a horizontal line connecting them both. And when we're considering moving from A to C, when we've got a UDL, we draw a straight line sloping down. So that's how we represent the UDL on our shear force diagram. That's meant to be a straight line, but it's hopefully close enough to a straight line so that you can see that. And we do exactly the same thing at the next point in our diagram where we are adding a point force. A point force, a point applied at a single point. So between C and B, there's still the UDL being applied, but the next point force is at point B. So let's look what happens at point B just before we get to it. So point B, let's see what happens just left of point B. So this time I'll raise this arrow here. This time, if you imagine our beam, we've come along from A. So we've got the force at A, we've got the force at C, the 10 kilonewtons down. We've come all the way along the beam to B. We're not including the force at B yet, so we're just to the left of that. And what we're saying is, what force are we experiencing? Total shear force are we experiencing just before we get to point B? And we add it up in the same way, and we consider all these points. So we've got 48.28, that's the force at A. We'll consider the UDL next. Well, we've got the whole beam, 9 meters worth, and it's 9 kilonewtons per meter. So that's total force due to that UDL acting down the beam is going to be 9 times 9, as we know from LS 81. And we've also got the force at C acting down as well. That's just 10 as it was before. So that's going to be 48.28 minus 9 times 9, which is 81, minus 10. And I'll put these into the calculator to get an answer here. So that leaves us with minus 42.72. And you might recognize that number because that's exactly the opposite force to the force that's being applied at point B. And that's what we'd expect because the shear forces are balanced out. We should be getting to 0 at the next point, but we'll just do the calculation to be sure. So that means the first point we're going to consider at B is down here, and that's minus 47.72. So what happens as we pass B, we get to the end of our beam, so it's just right of B. Well, we've got 48.28. All these forces from the first part just left. Minus 9 times 9, minus 10. But this time we're adding on the force at VB that we calculated previously, plus 42.72 kilonewtons. And of course, without this, we get negative that exact number. So add all these up together, 48.28 minus 9 times 9, minus 10, plus 42.72. And we're left with 0 kilonewtons. So the final force in our diagram is back to 0. So we've got a line vertically from minus 47.72 to 0. And like I said before, between points we draw a straightish, well, it's meant to be a straight line. There should be one continuous straight line here, if not quite. So you can do a slightly better job for illustration. You know what, I'll just draw it freehand. I don't want to waste too much time here, but we'll have a straight line coming down. That's not terrible, from there to there. And that's because when we have a UDL, there's constantly being the same amount of force added for every bit of distance we travel, but we know it's going to be a straight line, so we only need to work it out when we reach another point where we're applying a point force. So that's the shear force diagram that we have to consider. Now, the last thing we need to do is our bending moment diagram, and for the most part, this will be straightforward. But remember, the one thing that we always want to work out on a bending moment diagram is where's the point of maximum bending moment, and we'll come to that when we do it. But let's just rub out this here. I'll leave our shear force diagram on because we'll want to look at that. That's going to be helpful to us when we're doing a bending moment diagram for that exact reason. But let's just have a look at our bending moment diagram. Now I'll draw on another line on our page so we can represent that. Remember, this line represents zero bending moment on the beam. Like, here will do. Now, there's three obvious places to work out our bending moment straight away, A, B, and C, because they're points where forces are being applied and they're worth considering. Now, in previous videos, I've explained why it's a bending moment of zero at point A, and it's because our convention is we're looking to the left of the point and seeing what forces are being applied there. And from other examples, you probably know why B is zero as well, but I'll say zero, you can go back and look at other videos, but MB, the bending moment at B, I will show you that in this video here. So let's say a few things. MA, bending moment to A, is 0 kilonewton meters. There's nothing to the left of A, we don't need to consider that. MB, so that's the right-hand side of the beam. Well, let's think about the forces being applied here. We have a force of 48.28 being applied at point A. Now remember, relative to point B, this will be a clockwise force, so that's going to be positive. So we'll have multiplied by 9, that's the distance away from B. We'll have the force at C, which is a 10 kilonewton downward force, but that's applied at a distance of 7 meters, and it's going to be a counterclockwise turn relative to point B. So that's going to be minus 10 times a distance of 7. And then lastly, we've got the force that's due to the uniformly distributed load. And as before, we've worked out that it's going to be effectively 9 times 9, an 81 kilonewton downward force. And because we're looking to the left of B and all of the beams to the left of B, that's going to be concentrated at a point halfway along the beam. We're considering the whole beam here. So that's a point of 4.5 meters. Now this all should, I'll put this into my calculator just to double check, but this all should come out at exactly 0 because this isn't a cantilever beam. There's no moment being provided at point B. The beam is balanced. And on my calculator it shows 0.02, but that's probably just from rounding, because remember we rounded our force at 82 decimal points, so you can call that 0. It's just a rounding result there, so 0.0 kilonewton meters. So we've got the bending moment at B, and I'll mark those on our diagram just now because something that's hard to see when I'm putting things on at 0. I'll mark them at either end with red. So we've got 0 bending moment at A and 0 bending moment at B. Then the last thing we want to consider initially is what's the bending moment at C. So bending moment at C, let's look to the left. So to the left of C, you've got a force at A, 48.28 meters. But this is only 2 meters away from C. It was 9 above because B is 9 meters away from A, but C is 2 meters away from A. We don't consider the force at C because it's only things to the left and not things at C. But what is to the left of C is the UDL being applied over 2 meters. So the UDL acting down the way, so it's going to be counterclockwise relative to C. It's going to be negative. We've got 9 kilonewtons per meter. The distance between A and C is 2 meters, and we consider this halfway along that 2 meters. So the distance that this force is effectively applied at for determining this moment is 1 meter. And so if we put this into our equation, we're going to get 48.28 times 2 minus 9 times 2 times 1. And I'll just work out that value as well. So that works out at 78.56 in my calculator, which I think agrees with the answers. Terrible 6 kilonewton meters. So we can plot this point. Well, this is relative to our position C. So 2 meters along our beam, we've got a point here. This is, and we'll call this 78.56. We won't bother writing our units on, but we know they're kilonewton meters. Now remember, with bending moments, we plot positive values below the line to show the tensions being applied on the underside of the beam. Now, we know from previous examples when we're dealing with a UDL, it's not going to be straight lines in our bending moment diagram, it's going to be curved. And we could just draw a curve that went through the two zeros and 78.58, but that wouldn't be a good representation of what's happening. And the reason for that is we haven't worked out what the maximum bending moment is. We know it's not at C, because if we look at our shear force diagram over here, this is point C here. But we know from what we've considered previously in the course that maximum bending moment occurs when shear force is 0. So how do we work that point out? How do we work out how far along that is? So we'll call that distance from A to this unknown point. That's distance x. Well, let's think about the bending moment at distance x. So I'll do it here. There's enough room. I'll do it here. So bending moment, I've just got bending moment distance x here. So I work at the shear force at distance x. So we need this to be shear force is 0. So at distance x, the shear force is 0. So shear force at x, just SF I've written there badly, at x. Well, the shear force is going to be 0. So it's going to be equal to 48.28. The force at A still applies. The force at C still applies, the minus 10. And then it's going to be the UDL that makes up the rest of it. So it's going to be minus 9 for the UDL times x, so minus 9x, whatever x is. And that has to equal 0 because that's that point line. So we don't know how far along we are, but we know there's a point when we'll have taken 48.28, subtracted 10, we've got to somewhere past C, and we've got enough distance along the beam where the effect of the UDL is going to take our shear force to 0 before we pass across this line here. So what we can do is we can rearrange this equation, and that's going to give us 9x is equal to, let me get this right before I do it, 38.28. And that means that x is equal to 38.28 divided by 9. And that gives us 4.25 and then lots of 3s. But usually rounding to a couple of decimal places gives us enough accuracy. So we're going to say that x is right at the bottom of the screen is equal to 4.25. And that's in meters because our beam is measured in meters. So what we've done here is we've worked out the point where this is 0 must occur when x is 4.25 meters. So 4.25 meters. Now, I have run out of space a wee bit here. So what we're going to do is erase the bending moments I've calculated already. So this section up the top here. So if you're looking for this, the next bit of the video, just go back. I'm going to rub this out just now so we've got a bit of room to put in our bending moment at 4.25 meters, because that will be our maximum bending moment. And that will give us the final piece of information we need to complete this diagram and the question. So the bending moment at 4.25 meters, well, similar to the shear force diagram, we start from the left. We have the force at A, which is going to be 4.25 meters away from this point, because that's what the 4.25 meters means. So that's going to be 48.28 times 4.25. We've got the force of C to consider. Now remember, C is going to be 2.25 meters away, because if this point X is going to be about, I'll mark it in green on the main diagram, if it's going to be here and that's 4.25 meters away from A, that means it's only a further 2.5 meters, sorry, 2.25 meters away from C, because that has to add up the distance from A to C and then C to this point here. So 2.25 is the distance there. And so again, considering this turning moment, it's going to be negative due to the downward force at C. So we'll have minus 10 times 2.25 meters. And then the last force we have to consider at this point here is the force due to the UDL. So exactly as before, when we've done other moments in this beam, it's going to be minus because it's a counterclockwise effect considering this point X. It's 9 kilonewtons per meter, and it's at a distance covering 4.25 meters of beam. And remember, we consider it being applied halfway along that 4.25 meters. So half of 4.25 is 2.125. So we put all of this in. I'm going to work this out just now. And that's me redoing the calculation because I've definitely got it wrong the first time. And that's much more like what I was expecting. This gives us 101.41 to 2 decimal places kilonewton meters. So if we mark this on our diagram here, this gives us a point. I'm doing this approximately, but that's 78.6 we've marked already. This must be somewhere around here, which is 101.41. And that's going to be the highest the bending moment gets. So our curve should look a bit like this now. My best here. It should be curved. This isn't a straight line, it's a nice curve. It curves, and that's our peak, and it curves round through that point and back to 0. Now, it doesn't have to be perfect. What you're looking for in a problem like this is to get the bending moments at A, B, and C, as I've called them. You can call them what you like, and get the maximum bending moment and show that that's a curved line for the bending moment diagram, not straight lines. Straight lines only occur when we're only dealing with point forces. Because we're dealing with the UDL, because we have these diagonal lines in our shear force diagram, then we're going to have a nice curved diagram for our bending moment diagram. And that's the end of the question. So please, as ever, do feel free to contact me by email if there's any points in that you'd like me to go over further.